we continue our lecture for the second order system. Okay, before we go details into the second order system, there is one thing that I need you to take notes, which is the damping ratio, represented by the symbol of zeta. Okay, where the damping ratio is actually the exponential decay frequency over natural frequency. When we go for the second order system, you can see there is a different type of response for the second order system. We have undamped system, we have underdamped system, we have critically damped system, and we have overdamped system. You need to specifically define for the transfer function what are the response that you are expected for the response to behave. Is it undamped? Is it underdamped? Critically damped or overdamped? So basically, this this figure here is very important. I will use in the time response analysis. I will use it in the root locus analysis later on. So you have to digest this figure very much. So you can see, you can watch my video and second order system as well in YouTube. I have uploaded. So please refer back to the video and try to understand this very much. So we have sigma, and then we have j omega. So this is imaginary axis, and then this is the real axis. So for the second order system, we have the expression of prototype of the second order system is we have omega n square over s square plus 2 zeta omega n s plus omega n square. So this is the expression, general expression for the second order system, closed loop second order system. And then we see here, when we have a second order system, what does it mean is we have two poles. Okay? For the second order system, two poles. For the first order system, one pole. Remember last lecture, previous slides, we have first order system 1 over s plus 5. So s equals to negative 5. So only one pole for the second order system. For the second order system, we have two poles. So the pole's locations will define its response. Let's say, for example, we have pole that is located on the imaginary axis. So we have one here, one here. So when we have on the imaginary axis, we call the poles as a complex conjugate. Remember the imaginary expression? So you have, let's say you have A plus, let's say, B, J. We also have another one at A minus B, J. So this is a complex conjugate. So let's say we have one pole over here, we will have another pole down there at the negative J omega axis. So at this location, what will happen is we have here zeta equals to 0. So the damping ratio equals to 0. When we have damping ratio equals to 0, okay, when we have at j omega is actually we have the oscillation. At j omega we have the natural frequency. We have the natural frequency. And what we have is actually sinusoidal. The response would be something like this. So this is T, this is our amplitude, and then its sinusoidal becomes like this. And then what happened is this is sinusoidal is neither increase nor decrease, because the value of the damping ratio at this point of location equals to 0. So in this case, we call the system to be undamped. Next one. Let's say we have our poles now on the real axis. Let's say at this position, regardless of the value, negative A and negative B. At this location, okay, the value of zeta is greater than 1. And what you can see from the response over here, no oscillation at all. Because the damping ratio is greater than 1, it suppresses the oscillation of the frequency. Thus, we don't have any frequency and we don't have any oscillation at all. So it becomes something like this. This is what we call over damp. Now, let's say we have two poles at the real axis, but this time we have on the same location, meaning here we have two poles at the same location. Let's say we have at negative 3. So we have negative 3 and negative 3. At this point, zeta equals to 1, we don't have oscillation again, but the plot will be something like this. No isolation, optimal. And then we call this response is critically damped. Okay, critically damped. Finally, if we have poles that is located both on the real axis and on the imaginary axis. Let's say we have at this location. Remember, we have complex conjugate. Okay, if we have one positive, we should have another one at negative. Before that, I forget to mention that we will not consider right-hand side of the S-plane. Why? Because if the pole is located on the right-hand side of the S-plane, what will happen is the system become unstable. What does it mean by unstable? Unstable system is we cannot control it. We cannot control it. So if we press the button at 4th floor, I don't think we have control over it. Maybe it goes beyond the floor. It goes outside. We don't want the system to be unstable. So that's why we'll focus on the left-hand side of the S-plane. We go back to the last one. We have the poles that is located both on the real axis and on the imaginary axis. Okay, so at this point of location, the value of zeta greater than 0, less than 1. The response, we will have oscillation. So this type of response, we call it underdamped. So what you need to remember is zeta equals to 0, zeta greater than 1, zeta equals to 1, and zeta greater than 0, less than 1. Okay, at this point of location, the zeta equals to 0, and then when we change the pole's location, let's say we move it to the counterclockwise. So what we have here is this region over here is actually zeta greater than 0, less than 1. And then when it reach the axis, real axis, it will split one to the right and one to the left. So we'll have two poles location at different position, one to the right, one to the left, where at this position, this is what we call it as zeta greater than 1, and the response is overdamped. Before that, before it splits, it will have one location where we have at this point we have two poles at the same location, where at this point zeta is equals to 1. So at this point it is critically them. And basically, it is the values is actually mirror on the j omega and mirror to the real axis. So if we have one at this position, so we will have another at this position. If we have zero at this position, we will have another one at this position. To the right is unstable system.
For the underdamped oscillation, will there be any sinusoidal or there's no sinusoidal?
Underdamped.
The underdamped.
Ni sinusoidal lah.
The difference between underdamped and undamped, if both have sinusoidal.
Okay. The difference between underdamped and undamped. Okay, for the underdamped, the sinusoidal will eventually decrease to zero over time. Unlike the undamped, the zeta equals to zero, there is no ratio of to damp the frequency, the oscillation. So the oscillation will always remain the same. Unlike the underdamped. Underdamped, you have basically for the underdamped, you have the expression A plus minus Bj. Okay, this is a complex number. So the oscillation is actually caused by this j omega. The oscillation is caused by the natural frequency here. And then what makes the oscillation decays is actually the expression A here. The expression here is A here is actually it like the envelope to suppress the oscillation. Remember plot of the impulse that I have shown in the previous slide here. So this is what will it behave for the pole at the real axis. So when the time pass goes to infinity, the poles will decrease to zero. So this is actually the response of the poles at the real axis. However, when you have your poles on the imaginary axis, it will create oscillations. So if you have both on the real axis and the imaginary axis, so actually it creates oscillation plus decays. So that's why what you have is actually something like this, the oscillation. So the oscillation will be restricted by the value of poles at the real axis, something like this. So what I have just explained in the past 10 minutes, you can see from the lecture slides here, where let's say if we have general expression B over S square plus AS plus B, and then for the over them, you see the location of poles here on the real axis. So the system is over damped, and this is the response. For the under damped is both real axis and plus imaginary axis. So you will have oscillation that eventually decays to steady state values. And then for the undamped, it is on the imaginary axis. On the imaginary axis, no component of the real axis. We have only plus minus J3 in this example here. So there is no decays of the oscillation. And then we have critically damped, where we have the pole is located exactly at the same position, which is in this case is at -3. So the response looks like this. Okay, And then finally, we have the overdam. For the overdam is actually when we see we have the system, for example, we have a square plus 9s plus 9 over here. And when we find the expression 9 over, when we put it in another way, we have s plus 7.8, s plus 1.14. So when we put it into the time domain CT over here, we have the expression of K1, K2 exponential plus K2 exponential something. Okay, so here is actually, this is the force response. This is a force response, and then this is the natural response. These two, K2 exponential plus K2 exponential, here is the natural response. So you can see here the value of poles is actually the value of A over here. So remember A, just now we have negative exponential negative AT. So this A is it is a value of exponential frequency. So in this case, it's 7.85 and negative 1.14 over here. Okay, so I will explain underdam in details in next lecture, which is on Thursday. Meanwhile, please go back and watch the videos of the second order system that I have posted on YouTube. I have two videos, second order system introduction and second order system underdam. Please go back and try to digest before we go into details in next lecture on Thursday.